Hey everybody, it's Luke here at CMI, the Center for Manufacturing Innovation. I'm doing another podcast for Clemson University's Automotive Engineering Center, and I'm here with a student who works in 3D printing. Tell me a little bit about what you're doing and what these applications are.
So hello everyone, my name is Som Dixit and I'm a senior PhD student working under Dr. Shunyu Liu.
And we have a machine here behind us. There's a few machines we're going to look at. This is the first one of 3. We'll look at each of these machines, talk a little bit about how these machines work, and we have some 3D printed parts that we're going to talk about. So let's talk about this first machine.
So basically this machine, we called it as a laser direct energy deposition machine. So this machine is very good for fabricating the new materials. Like you can mix different kind of material powders like ceramics and also the metals, and you can fabricate the different kind of metal matrix composite. So talking about the machine itself, so this is the whole chamber. Inside this chamber the printing take place, and if you can see there is one head. Let me bring up the head a little bit.
Okay, I see the top piece moving, that's the head, bringing up.
As you can see, this head is a conical shape, and at the bottom of the head you can see there are 4 nozzles, copper nozzles. From these copper nozzles, the material, the powder material what we will insert in this machine will flow, and they will converge at a point, and that point will also be met with the laser that is coming from the top of this box. So basically what we do in this machine, we put the powders what we want to print. So these are the 2 powder hoppers. As you can see, I have put the powders inside these powder hoppers. There is an argon cradle you are seeing here. When we turn on these argon cradle, these powder hoppers will flow through these argon, and these powder will come through these 4 nozzles. And when they'll come from these 4 nozzles, they'll meet at a point, and at the top there is a laser which is meeting at that point, and that's how we are printing the part. One of the important feature of this machine is that whatever we are printing inside this box, it is completely an inert atmosphere. There is literally no oxygen inside it.
Got it.
If you see here, the current oxygen level within this box is only 0.75 ppm. So it's like 0.75 atoms of oxygen inside this box out of 1 million. So it's literally no oxygen atom present inside that.
Okay, so why do we have no oxygen in the box?
Yeah, so the reason is because here what we are doing, we are melting the material with the help of laser.
Okay.
So if you melt the material in not a good environment, then what will happen? The material will oxidize.
Okay.
We don't want any oxidation in the material, so for that we want the atmosphere inside this should be super good. So that's why we want to ensure that there should be no oxygen inside this environment. And you know, argon is heavy.
Yep.
So argon will settle down, and whatever the remaining oxygen level, oxygen atoms are left, they will go
pushed
at
to the top.
Yeah, and then there is this blower which will suck those atoms, and it will remove those atoms and again recirculate the good argon back inside this chamber.
Okay, so the argon is dense, and so that basically is like water filling up from the bottom, coming up to the top, displacing all the oxygen. It also carries the powder, right? So it's kind of like a carrier gas that uses, it's like the highway that carries the particles of metal into the injection apparatus. And then we have no oxygen because if oxidation took place, oxidation creates like a layer of rust.
Yes.
And if you have a layer of rust, that actually prevents the next layer of the metal you're melting from having a good adhesion and a good melt to fuse fully to the previous layer.
Yes.
So you're building layer on top of each other, and you got to have a clean surface for each layer to build on.
And that will also affect the mechanical properties, because when you will test the mechanical properties in kind of a tensile or compression, there will be oxide layer that will definitely reduce the mechanical performance of those printed parts. So we want literally no oxygen, especially for the materials like titanium and aluminum. We don't use it here in this machine, but especially for these materials you don't want any sort of oxygen inside this, because they are very highly attractive towards the oxygen atom, and you don't want that.
Yep.
So that's the basic overview of this machine. Now coming to the application. So what are the applications? The first very application is that you can print different class of materials while mixing them, right? So since I showed you 2 powder hoppers, right, you are literally mixing 3-4 kind of materials and put them in the powder hopper, and you will flow those materials with those 4 nozzles and you print them. So basically you are mixing different material and creating new kind of a material which should have a lot of application. Like the current material if you see, it's like a high entropy alloys. In high entropy alloys, you are mixing 4 different kind of a material at equiatomic ratios, and you are printing them.
So for people that are not familiar with the term high entropy, what is that? What are the mechanical, physical properties of a high entropy material that creates advantage for having that kind of material?
Yeah, so they are basically used in the aerospace application and the nuclear application, and these high entropy alloys, they have a very good wear characteristics, they have a very good oxidation resistance, they have very good corrosion resistance, and they have very good high temperature mechanical properties.
Okay.
So they can be used in the aerospace and the nuclear applications. So
like a space shuttle, for example, like extremely high temperatures on the surface, they might be used on the surface coatings for re-entry or something like that.
Yeah.
Okay.
So in short, if you want to say, we can say that this machine is capable of designing new materials.
Yep.
Which is a very simpler term.
Yep.
This can develop new materials, and the second very important advantage is that this machine can be used to repair the parts. So I went to the GE plant, and there I saw they were using this machine, and they were literally repairing the turbine blades. So in turbine blades, what happens sometimes with the time, these turbine blade tends to wear, and you need to remove the worn out parts. So if you want to repair that whole blade, that would be very costly.
Yeah.
You can directly, what you can do, you can cut the bad part from that turbine plate, you can mount the good part here, and you can directly print on the top of that part.
Oh wow,
so that is actually one of the great example, or one of the great application of this machine is to repair the parts.
Yep.
And also it this machine has certain properties that will create certain metallurgical dynamics inside those parts, that the repair process will adhere the same kind of the microstructural characteristics what the earlier part has.
Yep.
So that is the one of the 2 important application for this machine, like designing the new materials and repairing the part. And also you can do the laser cladding. So what is laser cladding supports? Suppose you have this, suppose with this example you want to, I'm showing this, you have this, it's like, suppose you can take it as an example where you can tell that this is some nickel part, and you want to coat it with some ceramic coating.
Yep.
So what you can do, you can just mount this part inside that, and you start rotating it, and from the top you are just supplying the mixture of ceramic and metal, and you can develop a coating on this top of this part. So you can also create the coating. You call that process as laser cladding.
Okay.
So that is the 3 applications for that this machine is used. So we have other machines also, like you can see it there.
Yeah, we'll go to that one next. One last thing is that because you have just this hopper, it's really easy to try different materials.
Yes.
It's just literally all you have to do is like pop off the lid and add the powder material of a different metal,
yes.
I assume.
Yes.
I mean, maybe you have to figure out some of the other chemistry with the carrier gas,
yes.
but it's really easy to test and test out different types of materials.
Yes, and how you can fabricate them, what are the properties they are exhibiting when you are fabricating those material with this machine. So I told you, like metal matrix composite.
Yep.
So you are mixing metal and the ceramic. You know, metal has good tensile properties, and ceramic has very good high temperature application properties. So when you mix them and you want to create certain material for the wear applications, you can create using that machine.
Yeah, I mean, I imagine, I used to work a lot in the automotive industry, and I'm still doing my PhD in automotive engineering, and I can see like turbos and turbine blades, like extremely high temperature, and one of these composite materials of like ceramics and metal, stainless steel or something would be really potentially high application. All right, let's move on to the next one. That was very cool. I learned a lot about laser printing and 3D powder metals. So this thing is big. It almost looks like a safe. It's got heavy big doors. I can kind of show guys on the camera here. Look how thick these doors are. It's like the thickness of my fingers. That's like 3 inches thick. It's got heavy big glass. It's got these big doors to block it. I guess these are access ports to use the gloves and the hands. And I think we unlocked it already. So I can pull this open here. Oh, it's like opening a big safe door. It's literally like, 3 inches thick. Okay, so tell me about this thing. I see the name right here says DMP Factory 350.
Yeah.
And it looks like a completely different setup from that previous one. So what are we looking at with this sucker?
So this machine, we call it as powder bed process. So in that case, you are feeding the powder. That's why you are calling it powder feeding process. This is called as powder bed process because what you are doing here, You can see this wiper.
Okay.
So what we do, we prepare the powder first. So we need to sieve the powder. So whenever we order the powder from, suppose in this machine we use Inconel alloy. So whenever we order the powder from the supplier, they send us the powder, we need to sieve that. Because why we need to sieve that? Because we don't want any powder which is oversized or undersized. So we want to use the powder up to a certain range. So we use the sieving process. There is the powder handling room.
Okay.
So after sieving that powder, we bring that powder here.
For those people who might not be familiar with sieve, I'm familiar with it because I actually used to work in geology. Geology uses sieve to get the right diameter size for particles of like rocks and minerals.
Yes, yes.
We use the same thing here.
Yes,
sieve is basically these like specific size like mesh to get a certain size material and for the diameter of the material into the machine. Okay.
Yeah. So after bringing the powder, this is the center portion. Here we mount a build plate, and then we bring this portion towards the bottom, and then we fill the powder.
Like a layer of powder metal, like you might have for like a kid's sandbox.
So
something.
then what happens, like after filling the powders, what we do, we generate the printing file also.
Okay.
So there is one software. So this machine is from the 3D systems. So we use their software. That software is provided by them also. So what we do, we generate a CAD file, whatever geometry we want to print.
Yeah.
We generate that CAD file. We import that CAD file into the software provided by this company, and then we generate a printing file. Suppose if I want to print this, so I will slice that part into number of layers. Suppose 1000 layers we want. We will slice that part into 1000 layers, and we generate that printing file for that part, and we'll insert that. So what will happen when I'll slice that into different number of layers? There should be certain layer thickness. Suppose 50 micron is the layer thickness. So what will happen? This thing, after filling the powder, this still will go up by 50 micron. This coater will move like this, spread a layer of 50 micron. Then the laser from the top will move at the location of that cross section, whatever you are printing.
Okay, so just to wrap up, or just to summarize what you're saying, you're still using a laser to melt the powder, just like the other machine.
Yes.
But instead of adding the powders, you have a bed of powder.
Yes.
And then this thing is just like a
spreader.
A spreader. It just kind of evens out the surface, a certain exact thickness.
Yes.
To whatever your sliced layer thickness should be.
And we call it as a layer thickness.
Layer thickness. Yeah. Okay, got it.
So we will do this process till the whole part is completed. Then we'll bring that up, remove the powder, and then we can extract that part out.
Yep.
So I can show you one example here. So this is one of the examples that I'm showing here is one of the printed parts that we printed using this machine. You can see these kind of lattice structures can also be printed with this machine. I'll tell you the exact application of this machine in the later part. Now coming to the application. So I already told you this machine has application in terms of design. So if you think about the design, the first thing came into your mind is the biomedical application. So in biomedical application, you need to print certain structures like struts or lattice structures that can be directly used as an implant inside the human bodies. It is heavily used in biomedical applications, aerospace industries also. So in terms of design, this machine is very good. Also, you can develop new material in this machine where you can like mix metals and ceramics or different kind of material, but
pre-mix them and then lay them in.
But in this machine, you need to mix a little bit material, right? Because the powder quantity, even if you have 400 grams of powder, you can print the part. But here you need to mix a lot of materials, right?
A lot more.
Yeah, because the powder bed, it's a big area you are printing.
Yeah, you're only using like maybe, I don't know what percentage. When you do the powder bed, it looks like you only use like 5% of the powder in the product, right?
Yes, yes.
Yeah. All right, let's go on to the third machine.
This machine is similar to that machine. It's also called as laser powder bed fusion.
Okay.
Only the manufacturer is different. So I think everything is same, just the process is same, the physics is same. Only the manufacturer is different, and maybe some specification in terms of laser, the maximum laser power you can go, that should be the different case. The rest,
okay, so the resolution, but it's all within the same ballpark.
Yeah,
it's not like an order of magnitude finer resolution. It's not an order of magnitude higher amplification or power. Okay,
Yeah.
And I see here some pretty cool parts. Like this one right here stands out at the top. This one says here, additive build medical. And you can see that's kind of like this very intricate, very fine mesh pattern they've built here. I'm not sure if that's just to is that used for any specific medical application, or is this an example of the kind of like print you can do and the kind of resolution you get out of it?
Yeah. So like if you see this additive acetabular hip cup, so you can see these structures, right?
Yep.
You can literally cannot make these structure from any other manufacturing process.
Okay.
Right. And why these structures are very helpful in biomedical application, because they help to grow the tissues. Because
okay. It creates a lattice for tissue to grow.
Yeah. Lattice for tissue growth. That's why this process is heavily used in the biomedical application.
Interesting.
And also you can see here some of the parts like these cube lattice structures cube. I think they are very fine, right?
Yeah, it looks like those are maybe some kind of bearing with a lattice structure.
Yeah, even I don't know what these are, but
okay, so basically, like, that's one of the cool things about 3D printing is that it literally opens up a whole new avenue for creativity and design.
Yes.
Because you can do things that a traditional CNC process, which is like a removal of material from the outside.
Yeah.
This is like building up internal structures. You could have complex internal geometries, channels, even like valves and other things, mechanical moving pieces that you could never make in traditional manufacturing ways.
And the other major advantage is that the material wastage is extremely low.
Yeah.
Yeah. So in case of like welding or in case of
CNC
any other
removal,
material wastage is very high. In this case, like you can like literally again sieve that powder and reuse it, recycle that powder and reuse it.
So if you're using really expensive, rare materials, this is a great application because you like reduce that cost.
And also energy saving.
Yep.
So I don't know the exact number, but it saves a lot of energy compared to the other manufacturing processes, because literally you are removing all those small steps in terms of the conventional manufacturing process, because here this process is giving you the part which is ready to use. You need very little post processing after printing the part, because the surface finish is extremely good. So that's the advantage of this machine. You can also call it as green manufacturing. I have heard that term. So so that's the advantage of this process. I hope I'll continue this journey in this process more and could help in developing this technology more.
Okay, so wrapping up here, we're, like I said earlier in the video, we're at Clemson University's International Center for Automotive Research. The building we're in is the Center for Manufacturing Innovation. And if somebody wanted to learn more about 3D printing with your advisor and your research group, what's your advisor's name again, and how can they get information?
Her name is Dr. Shunyu Liu, and you can just directly email her. She's very responsive in the email, and you can talk whatever you want to in terms of the technology, or if you want to work under her as a PhD or a master student, that would be really helpful.
Great. I'll put up the email link in the bottom here. I think that wraps it up. Everybody, thank you so much for checking out the video. Thanks so much for sharing with me your research and all the different applications. This is Luke with Clemson University Center for International Research. We're here at CMI, and thanks again everybody for checking out the video on 3D printing and all the different methodologies and tooling that we use for these 3D printing applications.
Thank you so much.
Thanks everybody.